We'll talk about the breadth first search. Breadth first search is one of the simplest uninformed strategies. It starts from the root, expands all nodes at depth 1, then all nodes at depth 2, and so on. They maintain the frontier or the fringe as a FIFO queue, first in, first out. Whichever enters first will be expanded first, and new successors go at the end. In other words, it actually does level by level, everyone in the first layer first and then everyone in the second layer in that order. This is done by keeping track of the frontier, as I said, as a FIFO queue, first in, first out. There is a small but important detail here. The gold test is applied when a node is generated, not when it is later expanded. This guarantees BFS finds the shallowest solution. But please understand, shallowest solution does not mean it's the best solution, but the shallowest solution it can find always. So that's called completeness. Let's discuss a little more about it. So here we show that how BFS works. The first A is expand and create frontier nodes B and C in the queue. Then B is the first one in the queue. So this is already visited. So now B will be expanded and will be added as D and E. And then C will be expanded and added as F and G. Okay, so C is in the queue after B. So when B is taken out, C is there, and then D and E are there. Then C is expanded, and after D and E, F and G will be added. So is it complete? Yes, BFS is complete. If there is a solution at some finite depth, D, BFS will find it. What about optimality? BFS is optimal if all step costs are equal. But it's not necessarily true always that all step costs will be equal. The first solution found will be the shallowest, hence the cheapest. So that means if all the nodes in the same depth are kind of equidistant from the root, and then the nodes at the second level are similarly equidistant from the first level, then only BFS will be optimal. What about the time complexity? In the worst case, BFS explores an entire tree up to depth D. I've already shown in a binary tree or a tree with B branching factor will be 1 plus B square plus B cube. In that way, when you sum up, it becomes order of B to the power D plus 1, which is exponential in D, which is the depth of the tree or the height of the tree, sometime called. So this will be the time taken, and this many nodes, all these nodes will be stored in memory. So the space complexity is also exponential, which is practically impossible to store it. So in summary, the time complexity is that BFS explores the entire tree up to the depth D. So that means order of B to the power D nodes. Big O of B to the power D nodes, rather, where B is the branching factor, and the space complexity is also that it stores all nodes in the memory about order of B to the power D, or big O of B to the power D space, dominated by the frontier. That means frontier means the last layer will always have the maximum number of nodes. You can see here, frontier means the children of a node. They are kind of contributing more and more as you go down and down. So why BFS can be impractical? This exponential growth is a huge problem. For branching factor B equal to 10, if B is 10 and the depth of D is 12, then it will be something like 10 to the power 12 or 10 to the power 13, which is a huge number. BFS would need about a petabyte of memory to store all the nodes, which is beyond what any PC can handle. Even if you had the memory, the time is also an issue. With a solution at depth 16, let's say D is 16 and B is even 10 to the power 16 plus 1 is 10 to the power 17, it could take hundreds of years to finish. So the lesson is, while BFS is simple, complete, and sometimes optimal, its memory and time blow up quickly. This is why we look for smarter strategies. Let's see how BFS can be applied on the Romania map. So just to give you some basic idea, if we want to go from Arad to Bucharest, and this is a graph search, so we know that initially Arad will be there, and then when we expand it, how many nodes to consider? So there will be Zerind, Sibiu, and Timisoara. Okay, so if I take like alphabetically, Sibiu, Timisoara, and Zerind. Okay, so initially there was A, and then we took out A in the FIFO queue. So let's say this is the queue. Okay, and then A was there, then we add S, T, and Z. Okay, then we will take out S because that's the first node, is first in first out, and then we'll expand to Arad is already visited, so we'll have Oradea, Reminsiu, Vilsia, Fagaras. Okay, 3. So Fagaras is first, then Oradea, then Reminsiu, Vilsia. So we'll add it here. After this, F, O, and R. Okay, so now T is before in this queue, so we take out T and expand it, Timisoara. So we can go from Timisoara to Lugos. That's the only place you can go because Arad is visited. So I add Lugos here. And then I take out the next one, which is Zerind. And if you take out Zerind, Oradea has already been visited. Arad is already been visited. So there is nowhere else to go. Okay. So now what we do, we have to see which is the next node, which is Fagaras. So we can go to Fagaras and see if we can expand it. Fagaras will be expanded to Bucharest and Sibiu. Sibiu is already visited. So Fagaras expand to Bucharest. So I add here in the queue Bucharest. Okay. So next is, so Fagaras is taken. Next is Oradea. Oradea have nowhere else to expand. So I don't expand Oradea. I take it out because Oradea has Sibiu is already visited. Zerind is visited. Now Reminsiu Valley, which is this, I take it out and expand R to Craiova and Pitesti. So this to Craiova and Pitesti. Okay, so I add C and P here. Okay, so so now I take out Lugos, which is L, and from Lugos we can go to Timisoara, which is already visited, and Mehadia. So I mark it here, Mehadia, and add an M here. Next I select B for expanding, which is Bucharest, and find out that Bucharest is the goal node, right? Bucharest is the goal node. So the search stops here, and then how many nodes it stored, you can see it stored A, S, T, Z, F, O, R, L, B, C, P, M. All the nodes are stored. Okay, so that's the way breadth first search algorithm works.